Learning objectives. In this chapter, the user would learn the following aspects of raw material. Get introduced to electronic components and electromechanical components. Understand diode operation and select diodes for various applications. Be familiar with active and passive components in real life. Panel sockets, switches and plugs, transistors, operational amplifiers and sample circuits. Understand various components. Identifications of components on the basis of size and shape. Electronics and system manufacturing. The first step is to identify the components. There are two steps to identify the components. By counting the number of pins in the component, the shape, color, material and any numbers on the component, and note the series of colored bands on the component. Understanding the specifications. The electronic components associated with Electronic Industries Association and Joint Electronic Division Engineering Council specifications. Design the electronic circuitry to ensure an adjustment range from normal adjustment settings of variable components. Provide a range of adjustments to compensate for composite variations in the associated circuitry. Types of components. There are two types of components: active components, passive components. Active components. These are devices or components which require an external source for their operation. Passive components. These are devices or components which do not require an external source for their operation. Active components. Some examples of active components are diodes, bipolar junction transistors, operational amplifiers. Passive components. Some examples of passive components are resistors, capacitors, inductors. Passive components. Resistors. A resistor is a passive two-terminal electric component which implements electric resistance as a circuit element. Resistors act to reduce current flows and at the same time act to lower the voltage level within the circuits. There are two types of resistors: fixed resistors, variable resistors. The unit of resistance is ohm. Sometimes the unit may be expressed in kilo ohms or mega ohms also. Color codes of resistors and power rating specifications. The following figure shows the color codes of resistors. The last band in the resistor is tolerance. The power rating specification of a resistor is given by the formula P is equal to V square by R. Thermal resistors. A thermistor is a type of resistor used to measure temperature changes, relying on the change in its resistance with changing temperature. Thermistor is a combination of the words thermal and resistor. Delta R is equal to K delta T, where delta R is equal to change in resistance and delta T is equal to change in temperature. Thermistor specifications. It is based on resistance at the operating temperature range, on the size and the time constant. Time constants are about 5 to 10 seconds. There are two types of thermistors: positive thermistors, negative thermistors. Positive thermistors. If the resistance increases with increasing temperature, the device is called a positive temperature coefficient PTC thermistor. Negative thermistor. If the resistance decreases with increasing temperature, the device is called a negative temperature coefficient NTC thermistor. Applications of thermistors. The main applications of thermistors, PTC, are used as a timer in degaussing coil circuits of CRT display, current limiting devices for circuit protections, used in digital thermostats. The main applications of thermistors NTC are food handling and processing industry, automotive applications, temperature sensor. Capacitor. A basic capacitor has two parallel plates separated by an insulating material. A capacitor stores an electric charge between the two plates. The unit of capacitance is farads, F. Capacitance values are normally smaller, such as μF, NF or PF. The formula of capacitor is given by C is equal to dQ by dV. Capacitor color codes. Capacitors may be marked with 4 or more colored bands or dots. The first two colors encode the first and second most significant digits of the value, and the third color the decimal multiplier in picofarads. The tolerance in capacitor is given by plus or minus 1%, plus or minus 2.5%, plus or minus 5%, plus or minus 10%, plus or minus 20%. Physical dimensions of the capacitor is given by C is equal to EA by D. Types of capacitors. The dielectric material determines the type of capacitor. Common types of capacitors are mica, ceramic, plastic film. Some capacitors are polarized. They can only be connected one way around. Electrolytic capacitors are polarized. The energy stored by capacitor is given by W is equal to 1 by 2 CV square. Applications of capacitors. The main applications of capacitors are electronic flash lamps for cameras, line conditioners, timing circuits, electronic power supplies, energy storage, pulsed power and weapons, power conditioning, oscillators. Inductor. An inductor, also called a coil or reactor, is a passive two-terminal electric component which resists change in electric current passing through it. It consists of a conductor such as a wire, usually wound into a coil. When a current flows through it, energy is stored temporarily in a magnetic field in the coil. The formula is given by L is equal to d phi by di. Types of inductors. The types of inductors are as follows: signal inductors, wire wound type; signal inductors, multilayer type; power inductors, wire wound type; noise suppression components, thin film type. Physical characteristics of inductance. The physical determination of inductance is given by L is equal to N square mu A by LC, where N is equal to the number of turns, A is equal to cross-sectional area of the core in meter square, LC is equal to length of the core in meters, M is equal to permeability of the core. Specification of inductance. Inductor specifications normally include the value of inductance, the current rating, and the accuracy or tolerance. Other considerations may include the temperature coefficient of the inductance, the stability of the inductor, the DC resistance of the inductor windings, the Q factor of the inductor, and the working frequency range. Due to manufacturing tolerances, an inductor is marked with a value of 100 mH. Inductors are usually produced with tolerances of plus or minus 5%, plus or minus 10%, or plus or minus 20%. Applications of inductors. The main applications of inductors are as follows: sensors, transformers, motors, energy storage. Transformers. A transformer is an electric device that transfers energy between two circuits through electromagnetic induction. The functioning of a transformer is based on two principles of the laws of electromagnetic induction. An electric current through a conductor, such as a wire, produces a magnetic field surrounding the wire, and a changing magnetic field in a wire induces a voltage across the ends of that wire. Parts of a transformer. The core, which makes a path for the magnetic flux. The primary coil, which receives energy from the AC source. The secondary coil, which receives energy from the primary winding and delivers it to the load. Losses in transformer. The losses of transformers are as follows: copper loss, core loss, hysteresis loss, eddy current loss. Transformer ratio. If N2 is greater than N1, K is greater than 1, then the transformer is a step-up transformer. If N2 is less than N1, K is less than 1, then the transformer is step-down transformer. K is called the transformation ratio of the transformer. N2, the number of turns in secondary windings. N1, the number of turns in primary windings. Types of transformers. There are many types of transformers. Some of them are as follows. Autotransformer. Transformer in which part of the winding is common to both primary and secondary circuits. Capacitor voltage transformer. Transformer in which capacitor divider is used to reduce high voltage before application to the primary winding. Distribution transformer, power transformer. Distribution transformers are used to distribute energy from transmission lines and networks for local consumption and power. Applications of transformers. Transformers have many applications in power transmission and electronics. They may be used to minimize energy losses due to voltage drop in transmitting electricity over long distances. They match loads with internal resistance so that there is maximum power transfer. They couple signals between electronic stages. Introduction to diodes. A diode is the simplest sort of semiconductor device. A semiconductor is a material with a varying ability to conduct electrical current. Most semiconductors are made of poor conductor that has had impurities added to it. The process of adding impurities is called doping. It flows current only in one direction. It is also called as unidirectional element. Operation of p-n junction diode. The interface between p-type and n-type material is called p-n junction diode. The barrier potential Vb is equal to 0.6 V for Si and 0.3 V for Ge at T is equal to 300 K. There is no movement of charge through a p-n junction at equilibrium. The p-n junction forms a diode which allows current in only one direction and prevents the current in the other direction as determined by the bias. DC voltage positive terminal connected to the P region and negative to the N region. It is called forward bias junction. DC voltage negative terminal connected to the P region and positive to the N region. Depletion region widens until its potential difference equals the bias voltage. Majority carrier current ceases. This is called reverse bias junction. As reverse voltage reaches certain value, avalanche occurs and generates large current. If an external voltage VA is applied across the p-n junction, the height of the potential barrier is either increased or diminished as compared to VA, depending upon the polarity of the applied voltage. The energy band distribution with applied external voltage is shown in the figure below. For these non-equilibrium conditions, the Fermi level can no longer be identified. In order to describe the behavior of the p-n junction, quasi-Fermi levels are introduced. Properties of diode. The transconductance curve on the previous slide is characterized by the following equation. ID is equal to Is e to the power of Vd by HVT minus 1. ID is the current through the diode, Is is the saturation current, and Vd is the applied biasing voltage. Vt is the thermal equivalent voltage and is approximately 26 MV at room temperature. The equation to find Vt at various temperatures is Vt is equal to Kt by Q. K is equal to 1.38 into 10 to the power of minus 23 J by K. T is equal to temperature in Kelvin. Q is equal to 1.6 into 10 to the power of minus 19 C. Applications of diodes. The applications of diodes are as follows. Ionizing radiation detectors. A single particle of radiation having very high electron volts of energy generates many charge carrier pairs as its energy is transmitted in the semiconductor material. If the depletion layer is large enough to catch the whole energy or to stop a heavy particle, an accurate measurement of the particle's energy is possible. These semiconductor radiation detectors require efficient charge collection and low leakage current. They are cooled by liquid nitrogen. Common materials are Ge and Si. Temperature measuring. The forward voltage drop across the diode depends on temperature. A diode can be used as a temperature measuring device. This temperature dependence follows from the Shockley ideal diode equation and is typically around minus 2.2 MV per degree Celsius. Zener diode. Zener diode is a silicon PN junction diode and it is designed for operation in reverse breakdown region. The basic function of Zener diode is to maintain a specific voltage across the terminals within given limits of load line or charge. It is designed to operate in reverse breakdown region. Two types of reverse diodes are avalanche and Zener. Heavily doped reduced breakdown voltage. It causes a very thin depletion region. Working of Zener diode. The circuit operates in reverse bias and operates in breakdown voltage. The reverse voltage VR is increased. The reverse current remains small. The reverse current is also known as Zener current. At this point, the breakdown effect begins. The internal Zener resistance, also called Zener impedance, begins to decrease as reverse currents increasing rapidly. Characteristics of diodes. There are two types of characteristics. Forward characteristics. The voltage is varied gradually and the corresponding current values are noted down. Reverse characteristics. The voltage is varied gradually and the corresponding current values are noted down. The diode allows electric current to pass in forward direction and block current in reverse direction. This is given by IV characteristics. The shape of the curve is determined by the transport of charge carriers through the depletion layer that exists at the PN junction. When a PN junction is first created, diffusion of holes and electrons take place through the junction. Applications of Zener diode. The applications of Zener diode are as follows. Zener regulation with varying input voltage, Zener limiting, voltage regulator, waveform clipper, shunt protection, peak clipper. Bipolar junction transistor. A BJT is a type of transistor that relies on the contact of two types of semiconductor for its operation. BJTs can be used as amplifier switches or in oscillators. BJTs can be found either as individual discrete components. Bipolar transistors are so named because their operation involves both electrons and holes. These two kinds of charge carriers are characteristic of the two kinds of doped semiconductor material. Electrons are majority charge carriers in N-type semiconductors. Types of BJT. There are two types of BJT. They are NPN transistor and PNP transistor. NPN transistor. NPN is one of the two types of bipolar transistors consisting of a layer of p-doped semiconductor between two n-doped layers. A small current entering the base is amplified to produce a large collector and emitter current. The current is carried by electrons moving from emitter to collector as minority carriers in the p-type base region. PNP transistor. The PNP, consisting of a layer of n-doped semiconductor between two layers of p-doped material. A small current leaving the base is amplified in the collector output. The arrows in the NPN and PNP transistor symbols are on the emitter legs and point in the direction of the conventional current flow when the device is in forward active mode. BJT characteristics. The BJT characteristics are as follows: CE configuration, CB configuration, CC configuration. CB characteristics. Input characteristic shows VCB dependence. Output shows breakdown at VCBO. CE characteristics. Input characteristic pretty good agreement. Output characteristic upward slope in IC, quasi-linear VEC dependence, breakdown at VCEO. Upturn prior to breakdown. Applications of BJT. The applications of BJT are as follows: amplifiers, temperature sensors, logarithmic converters. Transistor. A transistor is a semiconductor device used to amplify and switch electronic signals and electrical power. It is composed of semiconductor material with at least 3 terminals for connection to an external circuit. A voltage or current applied to one pair of the transistor's terminals changes the current through another pair of terminals. It was developed in 1947 by John Bardeen, Walter Brattain, and William Shockley. The transistor revolutionized the field of electronics. Applications of transistors. Transistors are used as a switch. In a transistor, no current can flow in the collector circuit unless a current flows in the base circuit. This property allows a transistor to be used as a switch. The transistor can be turned on or off by changing the base. There are a few types of switching circuits operated by transistor. Transistor is used as an amplifier. Transistor can be used to amplify current. This is because a small change in base current causes a large change in collector current. Operational amplifier. An operational amplifier is a DC coupled high gain electronic voltage amplifier with a differential input and usually a single ended output. Op amps are among the most widely used electronic devices today, being used in a vast array of consumer, industrial and scientific devices. It has 2 input terminals and 1 output terminal. Operations of operational amplifier. The amplifier's differential inputs consist of a non-inverting input plus with voltage V plus and an inverting input minus with voltage V minus. Ideally, the op amp amplifies only the difference in voltage between the two, which is called the differential input voltage. The output voltage of the op amp V out is given by the equation V out is equal to AOL brackets open V plus minus V minus brackets close, where AOL is the open loop gain of the amplifier. Types of op amp. There are many types of op amp. They are as follows: inverting amplifier, non-inverting amplifier, differential amplifier, hybrid amplifiers. Inverting amplifier. It consists of a resistor from the input terminal to the inverting amplifier input of the circuit and another resistor connected from the output to the inverting input of the op amp. The non-inverting input is connected to the ground. The gain of the op amp itself is very high and the output from the amplifier is a matter of only a few volts. This means that the difference between the 2 input terminals is exceedingly small and can be ignored. As the non-inverting input of the operational amplifier is held at ground potential, this means that the inverting input must be virtually at earth potential. As a result, this form of amplifier is often known as virtual earth amplifier. As the input to the op-amp itself draws no virtually current, this means that the current flowing in the resistors R1 and R2 is the same. Using Ohm's law, V out by R2 is equal to minus V in by R1. Non-inverting amplifier. In this circuit, the signal is applied to the non-inverting input of the amplifier. However, the feedback is taken from the output via a resistor to the inverting input of the operational amplifier, where another resistor is taken to ground. It is the value of these two resistors that govern the gain of the operational amplifier circuit. The gain of the non-inverting amplifier circuit for the operational amplifier is easy to determine. The calculation hinges upon the fact that the voltage at both inputs is the same. This arises from the fact that the gain of the amplifier is exceedingly high. The output voltage divided by the gain means that there is virtually no difference between the two inputs. The voltage at the inverting input is formed from a potential divider consisting of R1 and R2, and as the voltage at both inputs is the same, the voltage at the inverting input must be the same as that at the non-inverting input. This means that V in is equal to V out into R1 by R1 plus R2. Differential amplifier. Differential amplifier is a basic building block of an op-amp. The function of a differential amplifier is to amplify the difference between two input signals. The two transistors Q1 and Q2 have identical characteristics. The resistance of the circuits are equal, that is, RE1 is equal to RE2, RC1 is equal to RC2, and the magnitude of plus VCC is equal to the magnitude of VEE. These voltages are measured with respect to ground. The two plus VCC and VEE supply terminals are made common because they are same. The two emitters are also connected, and the parallel combination of RE1 and RE2 is replaced by a resistance RE. The two input signals V1 and V2 are applied at the base Q1 and at the base of Q2. The output voltage is taken between two collectors. The collector resistances are equal and therefore denoted by RC is equal to RC1 is equal to RC2. The output voltage is 0 when the two inputs are equal. When V1 is greater than V2, the output voltage of the polarity shown appears. When V1 is less than V2, the output voltage has the opposite polarity. Hybrid amplifier. Hybrid amplifiers are complete amplifier assemblies and contain internal bias circuits. The only requirement to power up the amplifiers is the application of one power supply voltage to the VCC pin. Hybrid amplifiers also contain internal bypass capacitors on the VCC line, and in many applications this is sufficient DC supply line bypassing. With the higher gain amplifiers or multi-stage amplifier, it is always good RF practice to add additional bypassing outside the amplifier module on the DC supply line. This also adds additional system power supply noise reduction. Depending on the frequency range of the amplifier, the bypass capacitors usually span the range of picofarads to microfarads in value. Characteristics of ideal op-amp. Infinite input impedance, low output impedance, very large voltage gain at low frequency, infinite bandwidth, low slew rate limited to 0.5 to 20. Differential input voltage. The amplifier's differential inputs consist of a non-inverting input plus with voltage V plus and an inverting input minus with voltage V minus. Ideally, the op-amp amplifies only the difference in voltage between the two, which is called the differential input voltage. The output voltage of the op-amp V out is given by the equation V out is equal to AOL brackets open V plus minus V minus brackets close, where AOL is the open loop gain of the amplifier. Characteristics of op-amp. Infinite open loop gain is equal to V out by V in. Infinite input impedance R in, and so zero input current. Zero input offset voltage. Infinite voltage range available at the output. Infinite bandwidth with zero phase shift. And infinite slew rate. Zero output impedance R out. Zero noise. Infinite common mode rejection ratio CMRR. Infinite power supply rejection ratio. Applications of op-amp. Piezoelectric transducer. Charge amplifier. Voltage error circuit. Proportional integral control circuit. Switches. A switch is an electrical component that can be an electrical circuit interrupting the current or diverting it from one conductor to another. A switch may be directly manipulated by a human as a control signal to a system, such as a computer keyboard button, or to control power flow in a circuit, such as a light switch. Switches may be operated by process variables such as pressure, temperature, flow, current, voltage, and force. Types of switches. There are many types of switches. Some of them are SPST, single pole single switch, DPST, double pole single throw, SPTT, single pole triple throw, DPDT, double pole double throw, DPCO, double pole center off, 2P60, two pole six throw. Switch explanation. Single pole single switch, a simple on-off switch. The two terminals are either connected together or disconnected from each other. Double pole single throw, equivalent to two SPST switches controlled by a single mechanism. Single pole triple throw, similar to SPDT. Some suppliers use SPTT for switches with a stable off position in the center and SPDT for those without. Double pole double throw, equivalent to two SPDT switches controlled by a single mechanism. Double pole center off, a DPDT or DPCO switch with the center position can be off in the center. The positions of such switches are commonly referenced as on, off, on and on, on. Two pole six throw, switch which can connect with a second switch, 2P, that is two pole, controlled by a single mechanism. Application of switches. The applications of switches are as follows: mobile phones, sample and hold circuit, networking, multiplexer, RF switches. Plugs. An electrical connector is an electromechanical device for joining electrical circuits as an interface using a mechanical assembly. Connectors consist of plugs, male-ended, and jacks, female-ended. The connection may be temporary, as for portable equipment, require a tool for assembly and removal, or serve as a permanent electrical joint between two wires or devices. An adapter can be used to effectively bring together dissimilar connectors. Plug and socket connectors are usually made up of a male plug and a female plug. Plugs generally have one or more pins or prongs that are inserted into openings in the mating socket. Properties of plugs. Electrical connectors are characterized by their pin out and physical construction, size, contact resistance, insulation between pins, ruggedness and resistance to vibrations, resistance to entry of water or other contaminants, resistance to pressure, reliability, lifetime, number of connect or disconnect operations before failure, and ease of connecting and disconnecting. Applications of plugs. The applications of plugs are as follows: used in industries, used in domestic. Domestic antenna plugs and sockets are devices that connect TV antenna cable to a TV set. Antenna plugs are male antenna connectors that fit into female antenna sockets. Antenna sockets are female connectors that have slots or holes which accept the pins or blades of antenna plugs inserted into them and deliver or receive TV signal to or from the plugs. Sockets are generally mounted on the TV set, or the sockets are usually designed to reject any plug. Panel control. A control panel is a flat, often vertical area where control or monitoring instruments are displayed. They are found in factories to monitor and control machines or production lines, and in places such as nuclear power plants, ships and aircraft, and mainframe computers. Older control panels are most often equipped with push buttons and analog instruments, whereas today in many cases are used for monitoring and control purposes. Control panel is a cabinet which contains electrical components to control the motors and equipments. Components in control panel. The main components in control panel are as follows: cables, bus bar, MCB miniature circuit breaker, MCCB mold case circuit breaker, ELCB earth leakage circuit breaker, incomer, selector switch, overload relay, timer, contactor. Cables. Cables are used for interconnection. There are two types of cables: power cables, control cables, power cables used to connect motor to panel component and panel to main supply. Control cables used to connect control circuits. Bus bar. Incoming supply is connected to bus bar and distributed from bus bar. It is normally made of aluminium. MCB miniature circuit breakers. MCB is a device. It is used before the feeder. This should be selected according to the capacity of the feeder. MCCB mold case circuit breaker. In most of the cases, the MCCB used as an incomer for higher capacity feeders for better protection. ELCB earth leakage circuit breaker. The ELCB is also known as RCCB, the device used for the protection against the earth leakage current and residual current. It should be fixed before the incomer. Incomer. The basic supply will be connected to this incomer. It also called as SFU, switch fuse unit. It contains one handle with fuse unit. Once it is turned on, the supply will pass to the next stage through fuse. If any major fault occurs in side panel board, it will trip and it will isolate supply. Selector switch. Selector switch is used for on-off purpose and for selecting the mode of operation like auto or manual. Starters are used for starting the motor safely. There are mainly two types of starters: DOL starters and start to delta. DOL starter is enough for the motors with power less than 10 HP. Overload relay. Overload relay is for the protection of motor from the overload. It senses the load current and trips if it exceeds the limit. Current limit has to be set manually. It should be 80% of the full load current. Timer. Operation of timer is similar to relay, but a delay is there for actuation. We can set the time delay manually according to our requirements. It is very much essential for start to delta conversion. Contactor. Contactor is an essential component in the control panel. It actuates when the signal from the controller, PLC, relay logic, comes. It is similar to relay. It is costlier than relay. It is used for a higher load. Integrated circuits. An integrated circuit or monolithic integrated circuit is a set of electronic circuits on one small plate of semiconductor. Integrated circuits are used in virtually all electronic equipments today: computers, mobile phones, digital home appliances, which have become inextricable parts of the structure of modern societies. This is made possible by the low cost of production of integrated circuits. ICs can be made very compact, having up to several billion transistors. Generations. There are 4 types of generations: SSI, small scale integration; MSI, medium scale integration; LSI, large scale integration; VLSI, very large scale integration. Small scale integration. The first integrated circuits contained only a few transistors called small scale integration. Digital circuits containing transistors numbering in the tens provide a few logic gates. SSI circuits were crucial to early aerospace projects, and aerospace projects helped inspire development of the technology. Medium scale integration. The next step in the development of integrated circuits, which was taken in the late 1960s, introduced devices which contained hundreds of transistors on each chip, called medium scale integration. They were attractive economically because while they cost little more to produce than SSI devices, they allowed more complex systems to be produced using smaller circuit boards, less assembly work, and a number of other advantages. Large scale integration. The large scale integration LSI in the mid-70s with tens of thousands of transistors per chip. Integrated circuits such as 1K bit RAMs, calculator chips, and first microprocessors that began to be manufactured in moderate quantities in the early 1970s had under 4,000 transistors. True LSI circuits approaching 10,000 transistors began to be produced around 1974 for computer main memories and second generation microprocessors. Very large scale integration, VLSI. The final step in the development process starting in the 1980s and continuing through the present was very large scale integration and continues beyond several billion transistors. Multiple developments were required to achieve this increased density. Manufacturers moved to smaller design rules and cleaner fabrication facilities so that they could make chips with more transistors and maintain adequate yield. Fabrication in IC. The fabrication in IC is as follows: silicon wafer, epitaxial growth, oxidation, photolithography, diffusion, ion implantation, isolation techniques, metallization, assembly processing, and packaging. Advantages of IC: small in size due to the reduced device dimension, low weight due to very small size, low cost due to large scale production, low power requirement due to lower dimension and lower threshold power requirement, high reliability due to the absence of a solder joint, facilitates integration of large number of devices, improves the device performance even at high frequency region. Disadvantages of IC. The disadvantages of IC are as follows. IC resistors have a limited range. Generally, inductors cannot be formed using IC. Applications of IC. The applications of IC are as follows: power amplifiers, small signal amplifiers, operational amplifiers, microwave amplifiers, RF and IF amplifiers, voltage comparators, multipliers, radio receivers, voltage regulators. Pin identification. There are many types of ICs in the market. Some of the main ICs in use are IC 741 and IC 555. IC 555 is used as a timer. When connected, each contact of a connector must mate with the contact on the other connector that has the same function. If contacts of disparate functions are allowed to make contact, the connection may fail and damage may result. IC 555. The IC 555 timer is highly stable device for generating accurate time delay or oscillation. The timer can be used with supply voltage in the range of plus 5V to plus 18V and can drive up to 200 mA. It is compatible with both CMS and TTL logic circuits. Pin diagram. The 555 timer consists of 8 pins. Pin 1 ground, pin 2 trigger, pin 3 output, pin 4 reset, pin 5 control voltage, pin 6 threshold voltage, pin 7 discharge, pin 8 VCC. Modes in IC 555. There are 3 types of mode in IC. They are monostable, astable, bistable, monostable. In this mode, the 555 functions as a one-shot pulse generator. Applications include timers, missing pulse detection, bounce-free switches and touch switches, frequency divider, and capacitance measurement. Astable. It can operate as oscillator. Uses are amp flashers, pulse generation, logic clocks, tone generation. Bistable or Schmidt trigger mode. IC installations. There are 3 broad types of ICs: through-hole mounts, surface mounts, and socket mounts. The first two involve soldering, but socket mounts do not. Soldering always begins with cleaning. The parts are soldered in place with several variations in technique. Finally, the part is cleaned again and inspected. Socketed parts can be removed and reinstalled, though care must be taken to avoid damaging their pins. Steps in installations. Clean the board with cotton swabs and alcohol. If any conformal coating is present, remove it with cotton swabs and acetone. The goal is to have clean pads so the solder adheres well and provides a high reliability joint. Install through-hole mounted ICs by first aligning the leads with the holes. Gently push the component into place. Apply flux to the leads and pads on both sides of the board. Solder the leads from the back of the board, the side opposite the component. Apply flux to the board to begin installing surface mount ICs. Carefully position the part on the pads and bring the soldering iron into contact with several to stick the IC in place. Clean up excess flux with cotton swabs and alcohol. Use magnification and look for any solder bridges or debris. Use wick to remove bridges. Exercise great care when removing or installing socketed components. Their pins can be easily bent or broken. Once bent, they can be straightened only once before breaking off. Use a chip lifter appropriate to the device. These can be simple levers or elaborate mechanisms, but their intended purpose is to prevent damage. Inspect the pins under magnification. Electrostatic discharge protection. Electrostatic discharge (ESD) is the sudden flow of electricity between two electrically charged objects caused by contact, an electric short, or dielectric breakdown. A buildup of static electricity can be caused by tribocharging or by electrostatic induction. The ESD occurs when differently charged objects are brought close together or when the dielectric between them breaks down, often creating a visible spark. ESD can create spectacular electric sparks. Principal sources of ESD in IC. Human handling system. A person walking on a synthetic floor can accumulate up to 20 kV. This voltage is discharged when the person touches an object that is sufficiently at ground. Test and handling systems. Equipment can accumulate static charge due to improper grounding. The charge is transmitted through ICs when it is picked up for placement in test sockets. ESD models. The model types are as follows: human body models HBM, machine model MM, charge device model CDM. Protection mechanism. Current limiting characteristics of N-well resistors. Impact ionization. Avalanche multiplication of PN junctions. First breakdown, avalanche breakdown of NMOS. Second breakdown, thermal breakdown of NMOS. ESD protection devices. N-well resistors, gate grounded NMOS transistors, GGNMOS, gate coupled NMOS transistors, GCNMOS, silicon controlled rectifiers, SCR, medium voltage triggered SCR. ESD protection circuits provide a low impedance path from input pads to the ground during an ESD strike to release the static charge accumulated on the pads. Clamp the voltage of the pads at a level that is below the dielectric breakdown voltage of thin transistors during an ESD strike. Provide very high impedance and low capacitance during normal operation such that it has a little effect on the operation of the protected circuits. Conclusion. In this chapter, the user has covered the following aspects of raw material: electronic components, electromechanical components, diode operation and select diodes for various applications, active and passive components in real life, panel sockets, switches and plugs, transistors, operational amplifiers, and sampled circuits.